All right. Hello, everybody. Thank you for joining. I'm going to start briefly about the things I do and how I look at the geoscience, and then I'm going to continue with the exact project that I want to talk about. So, urban data science. Personally, I'm an urban planner, so I always had to do something with the data and with the geo things. But it's just recently that I start really dealing with empirical things and using analytic tools to examine the cities. The urban cities are very complex topics. They consist of so many different layers, and it's not easy to understand them. And before, when I was studying, there was also a lot of talks about experts and predicting something, and also a lot of thoughts, how to build something, how to develop something, but there was not enough empirical evidence for that. So this is how we come to data. In the past few years, I'm dealing a lot with that, and I think that current cities and the technologies, GPS, different sensors, tracking, everything we have provide us huge amounts of data that we can clean, process, and get information out of that. And this is where the science come in. That means we can use the science and in order to process this information into knowledge and understand the cities better, patterns, and the way how to develop them. So I like to use this term with working with this approach. It's called the urban data science, and it's kind of something new and the way how I like to approach these topics. So this was a small introduction about the method, and I'm going to now present a project that we worked on last year. It was funded by the Dutch government, and it was about finding the ways for the low emission construction logistics for high-rise in Amsterdam. And we did a geospatial modeling approach. So this is why am I here, and this is why I'm presenting something, and I'm also here to learn more about the ways other people do it. So this is about the team shortly. It's a very big project, a lot of researchers around. I was a project manager and a lead researcher in that, but there are also many different people who dealt with the data collection, for example, and also need to give the props to Tsui, who actually did the whole coding, like the typing of the code. We did the conceptualizations of the model, and it was made by TU Delft in the Netherlands University, also University of Applied Science in Amsterdam, and AMS Institute, which is an instance that is kind of a broker between the academia and practice in Amsterdam. So they really tried to make the research applied. It's a very interesting institute, so you can check it out if you have time and interest. So about the context, I'm going to introduce the project, then I'm going to go shortly about the modeling approach, the way we use Python, and I'm going to try also on the way to explain why am I here, or like how I see it as an urban planner slash researcher slash coder, and how the whole project has been done. And some conclusions about the use of Python and the model, and I'm going to show you the model shortly. I hope I'm going to manage all in time. And at the end, I'm going to just show you the GitHub repository so you can have a look yourself. All right, so we start with the research problem. It's all about the emissions, especially in the Netherlands, which is a highly dense area. The government has huge issues with that because European Commission is not allowed anymore to produce more emissions, particularly nitrogen emissions. I'm not sure you probably know about the protest a few years ago, also in the past year, by the farmers. They really need to tackle the emissions, and this is what is the crucial problem. Also, on the other side, we have emissions that are high, and then we have a construction that also produces a huge amounts of emissions. And also, especially in the Netherlands, there is a huge issue with the housing. People can't find homes. It's overpopulated, so to say, in the terms of residential space. So the Dutch government wants to build, but at the same time, they want to lower the emissions. And this is where we kick in. We are looking at the logistics. Logistics are also crucial part into the emissions. They create a lot of them by transporting all the goods, by transporting all the materials, and we wanted to see how to lower the emissions in the future, in the next 10 years in the Netherlands. And we want to test these solutions and calculate the emissions. So some of the solutions proposed by many researchers are to build biobased, for example. Biobased timber materials are lighter. Also to build modular with the prefabricated elements, and they can also lower the transport flows. Also circular, that means local reuse of the materials, finding the materials locally so that we don't have to transport them from long distances, and also use of the zero-emission or the electricity-powered vehicles, for example, which do not burn fuel itself. So these are the proposed solutions that exist in the literature, and our goal is to see what is going to happen when they are achieved. This future state of these solutions we name BIMZEC. When they're bio-based, industrialized, zero-emission, and circular, and our model and our research want to see what is this amount of the emissions that we're going to save if we apply these measures. Slowly about research methods, we worked as a university together with the industry, with the logistic companies, with the designers, architects, and also with the government, in this case, the city of Amsterdam, where the case study is based. And we decided to use quantitative methods and to try to be as much as evidence-based, to gather the data that we have and to try to analyze it and visualize it. And the tool we decided to use for that was Python. It's accessible, people know how to use it, and it's also appropriate for the geospatial modeling. So a bit more about the topic. There are the construction hubs in the Netherlands, and also there is this concept of these. These are crucial because they allow emissions and name before, solutions and name before to be implemented. For example, if you want to locally reuse the materials, we need a place to store them, we need a place to remanufacture these materials, and for example, a circular hub could serve as that in the process. And there are also examples in Amsterdam, particularly this one is used as a storage. This hub allows water transport, also the water deliveries in Amsterdam, and it can have multi-functions. So in our model, we wanted to look at these strategies. We wanted to look where the hubs are located. We wanted to see how the materials are coming from the production place, from the factory, to the construction sites in the city. And this is a small graphical visualization of the things showing what do we want to model. And we want to model all the transport movements in the next 10 years and to calculate how much of these is needed to build what the government wants to build. So for that thing, this is why I'm here, we created this spatial model to test these so-called BIMZEC strategies. And this is an agent-based model. So a bit away now from the topic and to the technical things. I'm not sure if you're aware of the agent-based models. They're becoming very trendy in the past years, and they're, as it says here, computational models to simulate actions and interactions of autonomous agents in order to understand the behaviors of the complex systems. So when we have a lot of instances in the systems, in this case, for example, the construction sites, the suppliers, these hubs, we need to try to make a simulations, and these were the agents then. They have the rules also, how they interact with each other, and the environment, spatial environment where they are located, for example. And in the past year, they're really used to address these complex processes in the urban environments. This is just a small model. I wouldn't like to go into the details about these things, but this is a very famous segregation model created in the 17 years, and it is showing the racial segregation in a city, showing how people tend to live to the people who are more similar to them. And this researcher has developed that, and this is just a small case showing showing how the simulation is working. So people are the agents, and there's certain rules how they operate, and then you can see how the segregation starts. So we wanted to use something similar, and the logic behind this is similar in our model. Back to Python things, there is this Mesa library that we use for that. Mesa is created explicitly for easier computing of these models, and I'm going to say a bit more later how we implemented that. So a bit about the modeling. We have a fixed input, which is the high-rise construction for the coming 10 years in Amsterdam. This is already planned, and we know where the construction sites are. Then we have the logistics, materials that needs to be delivered to the construction site, and the model is calculating the total emissions of the logistics, amount of materials needed, and total transport movements. So this is what the model does. So 70,000 is the number of the housing that Amsterdam wants to build in the next 10 years. And here are the agents. So this is the first instance. These are the construction sites in the city. Agents are objects or the classes in the library, and this actually looks like this. We use the Mesa library to define each agent as an object, and they have also a lot of methods and in the inputs attributed to them. There are also suppliers. These are the places where the materials are coming from, so the origins. Construction sites are the destinations. Also, they're used as the classes or the objects. Then we have the construction sites. These are the nodes between the supplier and the construction site, and depending on the solutions applied, these can be used or not. So having a construction hub could maybe increase the transport movements or lower them, and we want to see how does that work. Also, they're also used as a classes in the model, and the demolition sites are only used when the materials are sourced locally. So when we use the circular approach, when we think that the materials are going to be found around Amsterdam, then the demolition sites are becoming the origins and not the suppliers anymore. So when it comes to the modeling, we created the parameterization. So this is also one plus of using Python in this case. All of these things kind of done could be essentially made in a linear way, but that wouldn't allow us to automate the things, and it wouldn't allow the user to create his own inputs. And by making these parameters, user can say, okay, there are no hubs in a city. Everything is transported by the roads. All the construction sites are made with a cement or with a conventional materials, for example, and none of the local materials is sourced. And then he can set up the parameters and see how the model calculates the total thing. But user can also make different scenarios, and we call it this as a create your own burger. You can also make a different subset of solutions and see what is the outcome of that. So we use this with the widgets and allow the user to customize the things. So we also made 6 fixed scenarios, which is scenario 0, the way it is now, and it goes to the future scenario when we think the most of it is going to be transported by a water, the most of it is going to be transported by the electric vehicles, for example, the most of the buildings are going to be based with the timber materials. So this is like this future, maybe utopian solutions, but the model itself allows us to play with the parameters and to see how the scenarios are developed. The model works very complex. I wouldn't go into these details. I guess it's already pretty much complex and not easy to understand all the parts. But there are also fixed input parameters or fixed input data that we found and entered the model. There is also data that is being calculated by the model, and the output data, which is the emissions, transport movements. And the model works kind of simply in a way that it tries to find the materials needed for the construction sites from the nearest suppliers, and the hubs are all included in the process when this is needed according to the scenarios. So we would then have a class which is also based on the Mesa library as an agent-based model, and it is created. This is what model delivers. So it's also very cool that this map hasn't been created statically by just like making the each map by finding own data, but it is automatically created in a script based on the parameters that user entered. And here we can see, for example, with the red lines, the roads that has been used and the amount, how much have they been used. We can also see the two large red dots that are showing the hubs that have been used in the process. And for example, the orange dots are all construction sites where the materials are being delivered. Yeah, this is also made during the data visualization using Folium, for example, that is connected to many different methods to get the data out of that. And I think that the data visualization is also very important for the stakeholders and for everybody who needs to read that to show them how the system would work. Yeah, as described, we have these agents. They're all part of the Mesa library, then later that creates the whole thing. There is also an environment in the model, which is the road network, zero-emission zones, the water wave that we implemented, so we kind of give the model a border, which is the geospatial dimension of it, and also the data landscape. So it was a very hard and long process to collect all the data needed, to clean it and to prepare it as the model output. And I'm just gonna go shortly through some ways how we get it and what does come into the model. For example, for the road network, we use the OSMNX, which is a very useful tool to download the road networks of the whole world. And also not only that, but also to define the road types, because for the logistics, trucks cannot go into through the smallest roads. So we only chose the wide enough roads to be used in the model. Also, the construction sites for the next 10 years, what is model based upon is used by the Geodata portal of Amsterdam. It's always great to use the local municipality or the local governmental portals for the data, but usually this is not available. We also need to do a lot of assumptions in the model, for example, for the suppliers to see where the cement, where the timber, where the aluminium, for example, is coming from, where these geolocations we needed to make an assumptions and to choose always the closest supplier in the region, which is not very realistic, of course. And also some of the data is based on the previous research. This is from my colleague, to predict the future locations of the hubs, for example. This is then always based on the previous research. So again, the assumptions. Also, we based certain things on the scenario studies. Also for the logistics, we needed to see what vehicles are used for what materials, what are the amount of emissions for each vehicle, per each kilometer, and we also spoke to a lot of experts in order to find these things out and also to see how it works locally in Amsterdam. Yeah, and these are the final results of the model. We can see different emissions. We can see how each of the scenarios from 1 to 6 is creating either lower or higher emissions. So in the first case, the emissions are pretty high. In the last case, they're pretty low. But in the mean, there are certain not planned events, I would say. And I'm just going to go briefly to some of the results. For example, we saw that these hubs allow to transport with the water, and that reduces the CO2 emissions in the scenario 2. And also, we also saw that the circular economy leads to much lower emissions on a large scale because materials don't need to be transported from long distances. But then at a certain points in a space, we can see a huge amount of the rise of the local transport movements, which could impact negatively the local environment. And these are some about the Biobased building. This is about the modular buildings that they could possibly reduce emissions. So we can see how the model brings certain results, or how model can make a certain predictions where in the future we should go, or if we do something in this way, what is it going to mean for this city. About the model dependencies, there is a huge amount of libraries we used. It's either the Mesa library for the agent-based modeling or the data wrangling libraries, pandas, numpys, also spatial geometries, but also a lot of these for the visualization. So it's really based on the dependency, and this is why Python is used. Also, there was a process with the model testing. Still not all options are tested, so because we have the parameterization, there are so many different potential combinations of the parameters, and it was happening that the model is just crashing for the certain combinations. So this model testing, after the model was done, it took a long time to complete. Also, we did the validations with the partners. This was a validation with the municipality of Amsterdam and some local logistic companies to see what do they think out of the model, can it be used, or what should be improved for that to be used. So I always look at this from this perspective also a bit, not just as a coding, as something with the numbers, but also how it can be applied. This is I think, very important aspect. And yeah, also the data. The data was very messy. It was also a long process to organize, to conceptualize it, and also to make it reliable. Yeah, the model limitations are that the data quality is not always good. We also needed to create a lot of data, so to generate it in order to make it as an input data for the model. We need also to simplify a huge amount of things and to make a lot of assumptions that this is work in a way we made it. And also it needs to be validated more, and we also needed more time to do it. So there is it's a never-ending process, but we also wanted to model, for example, the impact on a city. So what would be all transport movements that we found? What would be the impact on of the noise, for example, in the neighborhoods of these, but we didn't have time for that. Yeah, and this is what the model delivers. I'm going to show you also in another browser, but it delivers the charts. It delivers also this map where the user can see how the emissions are changing through the year and what are the total materials used, for example, what is the hub doing in the process. And also I would like to recommend Voila. I'm not sure if you know about it. There is going to be a presentation later where you can use this library, put it in a code, and just like very fastly render the results in this way. And also with the binder, you can also then reshare it with everybody around without the code. And right now what we're doing is that we are developing a small web app that can be reshareable with the stakeholders, with the people who are not coding, so that we can also get a bit more attention about the things done. And all the charts were made before with Plotly. So by integrating it with Plotly Dash, this can be made into a proper web app. And currently there is a work in progress on that. I'm just going to want to show you. I'm not going to run the model now because it lasts for a minute or two to calculate the things. But this is all used with the Voila, as I showed before. And you can see the name and then the 6 scenarios. I said the scenarios are made out of 6 parameters, and user can either look at these parameters or create his own parameters and set up the things here. The Biobased type, the trucks types used, and when the user starts the model, this is going to be the outcome. The total emissions, NOx emissions, CO2 emissions, different material compositions, CO2 emissions per material. So we have a kind of a different charts, and the user can also look at the map and see which places are mostly where the most of the trucks go, for example. And this is another way when the water transport is used, when the local circular materials are used, and you can see kind of a huge increase in the number of transport movements, for example. Yeah. And yeah, to end up shortly, all models are wrong, some are useful. I guess all of you know this quote. I'm also thinking a lot about that. So this was my first modeling work, and I was also confused a lot of times, and I'm still a bit confused with the things done. Kind of there's like a lot of elements into that, geospatial data, Python modeling, also some applications. But I'm like thinking all the time, like, what does that really mean? And is this model really useful or just a bit useful? And just to conclude about the Python, I think it's very good that we can use this code because it can be reusable, shareable. We can also use the things that other people did before, and it's very optimal for the work with data modeling and urban geospatial stuff, especially because of all the libraries that we have right now. And about the conclusions about the model and the work done, I'm thinking, okay, what does it mean? As I said, like, can we really apply it in the real world solutions? I think that it should involve more public and private stakeholders, and there should be much more research on that. So I'm all the time thinking, what now? Like, good, we have the models, they can do something, they can predict, but is it good enough? Should be developed more? And yeah, I would like to finish with that. Thank you very much, and you can have a look yourself at the things, and there is also a full model on the GitHub repository. Thank you.
Thank you, Peter, for this very exciting talk. We have a few minutes for questions. Are there any questions in audience?
Hi, thanks so much for the presentation. I'm wondering whether the model, do you think, can be used for other cities? I guess like the input data, the data collection is kind of a big obstacle. You will need to collect all the data for a new different city. But like how the model works, do you think it could be applied in another city?
Yeah, I think that that's a good question. Usually when I was doing something before, the things could be easier applied than this, because I mean, if you have the data and if you just can change this a few CSV files that the model takes in, then it can work for any other space in the world. But it depends on the data used. So I'm not going to go all the way back, but if the city has, for example, the plan for the future construction for the next 10, 15 years, then yes. If we have the roads for the city, then for example, yes. But there are certain things that should be also examined. So I think it's not easy to apply it instantly in another city. Maybe in the Netherlands it's easier, but in other states, I think there is a work to be done. Yeah.
All right, thank you. Do you also take like an economical cost into consideration, because that is probably the driver on the other side to balance things or look for an optimal?
Yeah, good. Thank you very much for that question. This research was done kind of very utopian, so very future predicting. It was only 1 year long research, and the economical cost wasn't included. My fellow Tanya, she did a similar thing, but only for the hubs. She looked at the optimal scale for the hubs in the region of Amsterdam to see where to position them, but in regards to the cost. So like what is the kind of, she made an index CO2 emissions per euro or CO2 emissions per certain monetary value, and this is where it gets a bit more realistic. So the cost could be a big issue here.
Okay, then maybe one last question from me.
Please.
How does this fit into the concept of digital twins, and where do you see kind of synergies between these two, I guess, at the moment parallel things, like simulating into the future and doing digital twins of construction sites? So like, would you say that the digital twin is something like this, but with the real-time data, or I think that like there is a kind of a lot of ideas about making a control tower and kind of connecting the local logistical partners and the cities and the hubs into a very, very sophisticated optimization of all the rights in order to make this happen. So maybe I would say this is a simulation, this is just showing what could happen. And then the next step is to say, okay, if this is really so good, if we can really save that much of emissions, then we would need a digital twin, and we would need really integrated systems to make them happen. So I think the digital twin is a step to the closer to the implementation. Okay. Good, great. Thank you, Petar.
Thank you very much.
One more applause.